Hello everyone, welcome to these tutorials where we are focusing on statistical analysis in Python. In the last tutorial we looked at comparing two groups using non-parametric tests. We looked at Mann-Whitney U test, for example, and looks like a lot of you liked that specific video, and in general I see a lot of engagement with these statistical analysis tutorials. And in the last one, a few of you asked me questions about how about comparing two groups of time series. Obviously they're not completely uncorrelated, right? So two groups of time series, how to handle that, and exactly the reason why I have recorded this video. Obviously this wasn't part of my original plan, that's why it says tutorial 5B or 363B as part of my series, because I've already recorded 364, 365. So it only makes sense for me to include this or insert this. So here is a high-level plan. But I should mention, if you really like these videos, again, if you want to be notified, this would be a great time to pause right now, hit the subscribe button, and while you're there, try to find that little thanks button if you're feeling extra generous. Okay, so the plan here is first let's look at why do we even need a different type of test. If you have parametric and non-parametric tests, why do you need to do something else with time series? Well, the problem with traditional test is the standard test, like Mann-Whitney, for example, they assume data independence, which means each data point is unrelated to the others. But in time series, that's not the case. By definition, time series means something happened at time t equals to t minus 1, right? So by definition, today's price, for example, if you look at stock prices, today's price depends on yesterday's because it builds on yesterday's, right? Whether it goes up or goes down, it doesn't matter, but it relies on yesterday's values. So that breaks this rule about data points being independent. And of course, temporal autocorrelation is kind of common, and of course it leads to false conclusions. So this is the reason why we need to not use a completely different test, but need to address these aspects of autocorrelation before applying the Mann-Whitney U test. So we are going to look at 4 of these. One is naive method. The first one, naive, basically we just ignore autocorrelation and we just use baseline comparison. Probably it works because autocorrelation is not as common as you think, even in time series. So probably the baseline comparison actually works. I mean, the naive method works, but I always do this as a baseline. And then you do pre-whitening, right? So what does that mean? Of course, you remove the correlation first. If there is any correlation, of course, you can apply models like ARIMA and SARIMA if you have seasonality in your data. These are autoregression based methods, and you'll look at that in a minute, but I have done a few videos in the past on time series, on ARIMA and SARIMA, and the entire time series aspect. So please look for those videos on my channel. But for now, we are going to apply, let's say, ARIMA, and then kind of fit our data to this autoregression model, and then remove that correlation, and then only look at the residuals to actually apply our Mann-Whitney U test, right? So this is correlation, and which is true for actually stock data. And dynamic time warping alignment is another approach that we will look at. And again, it aligns patterns optimally and then look at time differences. What the heck do I mean by that? Wait for the next slide. But DTW basically means dynamic time warping. And block bootstrap is the third approach that we'll look at. And here, as the name suggests, first of all, bootstrap means randomly sampling from your data. Okay, and then reconstructing your data. Block bootstrap basically means instead of taking individual data points from your time series data, because you take random blocks at a time. Obviously, because you want to preserve that time correlation in your data. So instead of sampling random, you sample blocks. Random data points, you sample random blocks. You'll see that in a minute again. So just a quick note about dynamic time warping. This is a technique that people use, for example, when you look at speech recognition, let's say. So what do we mean by that? Well, first of all, the problem is you have two similar patterns with different timing. when I speak, sometimes I speak slow. Sometimes I speak very fast, right? But it's still me. So when you try to recognize this voice, obviously you need to either compress or slow down my speech and then perform some sort of a speech matching recognition, right? So that's where dynamic time warping actually comes from. And this is where the standard comparison fails to detect similarity. So what does dynamic time warping? Look at the graphic on the right hand side. Top and bottom are basically, let's say, identical, except here it's compressed a little bit. And once you warp it, instead of straight one-to-one mapping here, in other words, if you're finding the distance between that data point and this data point, if you only look at the straight line distance, then it's basically a rigid distance between those two data points. Now we are actually warping it to make sure these approximately match. And then you are actually looking at this distance between these two. I hope that makes sense. As you can see here, you're expanding it. And at some places, you're contracting it. The data points. So this is what dynamic time warping basically means, right? So find optimal alignment between the time series and allow stretching of this time or compressing of the time. And then your mapping between these two is warped. That's where the term warping comes from. And once that's done, you can warp the time series, like I mentioned, and create the aligned data sets. So once you correct for that, you have two aligned data sets. Now you go ahead and apply your Mann-Whitney U test, for example, on this data set. But one key point here is this does not change the statistical test itself. It just pre-processes your data so that you remove any of these timing differences, and then you're applying your Mann-Whitney U test. So previously, we removed auto-regression. In this test, we are removing any time changes. So that's basically it. Okay, I think it's time to jump into the code and go through some of the notes, and hopefully this won't turn out to be a very long video like some of my videos. So let's go ahead and jump in. And I zoomed into this quite a bit, so hopefully you should be able to see the text. I'll share the code so you can actually go through this yourself, but I added a lot of notes. As you can see, of course, the goal here is the time series statistical comparison, and the top part is basically what you saw in our presentation, and we are going to work with naive approach. Of course, this is what not to do when you have time series. Yeah, a basic Mann-Whitney U test without doing anything. And then we do some pre-whitening. Of course, I mentioned that. Remove temporal correlation. Let's use ARIMA models for now. And then go ahead and perform your Mann-Whitney U test, right? So again, the idea here is if we remove the time pattern, then we can actually use standard tests on the residuals, whatever is left over. And then dynamic time warping, I just talked about this. And block bootstrap is also, I kind of mentioned, summarized just now. So you just take individual blocks, shuffle the blocks, so you do have consecutive time points within a given block, and then perform your U test. Okay, in this example, we are going to use Apple versus Microsoft stocks. I don't anticipate much of any difference between these two. That's why this, I think, is a good test, because both are tech stocks and both tend to go up or down unless one of these companies screws up or does an amazing job, in, I don't know. So you'll have always some, ups and downs, but on average, they should go up or down responding to the market conditions, because they both are pretty much the technology stocks. Tesla may have a bit more volatility. Probably same with NVIDIA. I'll let you guys change those. Just search for Apple, in this code, and replace it with whatever you want. Or even non-stock data. Go ahead and test that out. Expected outcome, I just put that here. They may show no significant difference. I know they should not show significant difference because these two are such close. They should be, other than the price itself, the percentage ups and downs should be pretty much similar. Okay, so let's go ahead and install Yahoo Finance so we can actually get the data sets from there. And DTAI distance, and this is basically our dynamic time warping distance application right there, and stats models, as you probably saw in the last couple of videos. So let's go ahead and import our library. And again, from stats models, I'm importing ARIMA. So we are going to subtract fit our data to ARIMA model right there. That's where that comes into picture. And DTW, I'm using DTAI distance library for that. I just mentioned about it. Okay, let's go ahead and download the data. So I am downloading Apple and Microsoft right here. And between 2022 January 1st and end of 2024. And we are going to look at the close. Of course, that's what makes sense. At the end of the day, what's the stock price right there? And then I'm converting that into a percentage change, basically, compared to the previous day, right? So that's, and converting that to percentage, basically. So this is our return percentage values right there. And this is what we are actually using from now on. And then at some point, I believe I'm doing correlation right there. So I can, this is basically a Pearson correlation. If you watched 2 videos ago, you know what I'm talking about. And we're going to print that on the screen. Is the correlation, between these two, 0.2 or 0.6, like how well are they correlated? If it's above 0.5, just to remind you, that's a good correlation. So let's go ahead and run this and look at the plots. First of all, the data, we have 732 data points, of course, Microsoft and Apple. And if you look at the stock prices, the orange is Microsoft and the blue is Apple. You see, they kind of have a similar, sometimes you have like some extra activity going on for one of these, but on average I would say Apple is a bit more volatile compared to Microsoft doesn't look as volatile. But if you look at daily return percentage, if you plot them, I don't see much of a difference between Apple and Microsoft, right? I say I don't see. That doesn't mean anything. You have to perform statistical tests to confirm. My opinion doesn't matter. That's why we have statistics, right? So now these are, and when I performed the correlation, I got Pearson correlation value of 0.68 or almost 0.69. That's a strong correlation between these two. And visually we can see that right there, actually, to some extent. So that's a strong correlation. And if I plot the return percentage versus the frequency plot right there, it's almost normal distributed, as you can see, for both of these, and they both are almost overlapping on each other. So visually we can tell that, okay, they both are almost behaving exactly the same, right? But again, we have to first check autocorrelation and a few other tests. Now, how do we check autocorrelation? Again, you have this Leung box test, and to detect the temporal correlation. What does that mean when we apply this test? We test whether a series of observations in a time series or over time are random and independent, or if they're not. That's basically what that test actually tells you. And we are visually, we want to confirm this. So we're going to plot the autocorrelation functions. And again, in case you don't know, autocorrelation basically refers to a measure of similarity between a time series and then a lagged version of it. Like how about you go fast forward 10 days? Like what is the similarity between these two for that same data set itself, right? Over these next few intervals. I hope that makes sense. And then we can apply our standard test and see if they are biased. I'm showing you the result ahead of time because obviously I did run this code and I got a value of p.025 for Microsoft, and for Apple I got 0.626. Right away you can tell 0.626 is obviously much greater than 0.05, which means we cannot disprove our null hypothesis. Here we do disprove our null hypothesis because it's technically less than 0.05, but it's so close to 0.05, we still need to kind of consider, okay, maybe this is not enough. So let's go ahead and run this and then look at the result. So checking autocorrelation, and again, these are from stats models.diagnostic. You have the test right there. So no need to write any code, right? We are just using a library right there, and we are lagging by 10 days right there. And then we are checking autocorrelation. And if the autocorrelation is less than 0.05, then we say, okay, this null hypothesis has been disproven. Otherwise, there is no significant autocorrelation, right? So, or in other words, what do I mean by null hypothesis disproven? That means the autocorrelation is detected. Otherwise, we assume that there is no autocorrelation, right? So that's where we are, and then we are going to plot, basically. And we are checking for both Apple and Microsoft. So we did already run that test. So it gives us for, like we already mentioned, for Apple 0.6257. That means there is no significant autocorrelation. So there you go. So that's the lag by 10 days. In fact, right after the first data point, it kind of falls down right here. And here it is day-to-day returns. If you visually look, Microsoft looks almost identical to Apple, although its p-value actually coming up to 0.0247, so technically less than 0.05. So statistically, we should say autocorrelation detected because our value is less than 0.05. Okay, so in this case, autocorrelation detected. In this case, no autocorrelation. Great, fine. But let's go ahead and perform our naive comparison. This is just checking whether autocorrelation exists or not. We'll take care of that in a minute. So let's do our naive comparison, which is basically we are applying Mann-Whitney U test. It's very straightforward. We have done this many times. I mean, we have done this in the last tutorial. We are importing this from our library, and we are just applying Mann-Whitney U. And to it, we need to supply series 1, series 2, and then, we get our stat and we get our p-value. Now, just to summarize this, we actually get a p-value of 0.921, which is, of course, greater than 0.05. What does that mean? That means or what not to do baseline, or the naive baseline is giving us the result that we expect. Even though it may violate the autocorrelation or some other rules. So, but this is our baseline. So let's go ahead and check. So in one case, the mean value, none of that matters. Our p-value is what matters in this case, right? 0.92. That means basically our null hypothesis of both these data sets are not significantly different is not disproven. That's a double negative, but what that basically means is there is no significant difference between these two data sets. Okay, so that is from our naive comparison. This is what we get. Now let's actually do our pre-whitening approach, which means we are fitting ARIMA. In this case, we are using 100 model, which is basically a first order autoregression model. In other words, we are going to fit this to an equation where it's based on linear combination of the previous value and a constant plus. So my today's value equals to previous value multiplied by something plus a constant term. Okay, and once you fit that, extract residuals, you subtract that and you extract the residuals. And now apply Mann-Whitney U test on the residuals, and if that U test actually proves or disproves your null hypothesis, then you can make some sort of a judgment about the data. That's it. In our case, again, looking ahead, our key insight, our p-value is 0.8, again, much greater than 0.05, which means, our original autocorrelation was weak to begin with, right? So did we look at those values, autocorrelation values? I thought we will look at those right here. But our pre-whitening had minimal impact on results, right? I mean, our p-value here is 0.882. Previously, we got p-value of 0.92. Pretty much similar p-values with auto-regression fitting or pre-whitening approach, or with our naive approach. In both cases, it's very similar. So after removing these temporal correlation patterns, or pre-whitening, we'll find that the clean data that we're going to get from Apple and Microsoft look statistically indistinguishable. So that's what we will look at. I don't know if you guys like me putting like the expected result up here. I'm trying this for the first time because I thought adding notes ahead of time is better than going down and then adding notes, which interferes with the notes of the next block. And this is something I'm trying. If you don't like this, go ahead and reorganize it. It's obviously pretty simple. Okay, so we are actually applying this ARIMA onto our series with an order of 100. And again, this is our first order ARIMA that we are actually fitting. And then you're getting the residuals. Once you have the model fitted, then you can actually get the residuals after fitting it. And that's exactly what we are looking at, the residuals. Okay, and then we are applying the autocorrelation, right there. Okay, so we did already run that. So if you look at the autocorrelation coefficient, like 0.01 minus 0.01, that's such a small value. So there isn't much autocorrelation going on in these two data sets, both Apple and Microsoft. So that's why applying a correction, not applying a correction, you don't see much of a difference. And that's basically what the summary was earlier. Now we haven't. This is just extracting residuals. We haven't performed the test yet, right? So basically here we just check that if the residuals are white noise, but let's go ahead and compare the test right here. I mean, between pre-whitened and the naive tests, I guess. But all we are doing here is applying our Mann-Whitney test on both residuals. That's it. This is the key point in this block. And of course we are plotting. So let's go ahead and run this code to see what p-value do we get for our Mann-Whitney U test on the residuals. And if the p-value again is greater than 0.05, then of course both data sets are equal, or otherwise they're different. So let's go down, and the p-value is 0.88. I already mentioned that earlier, and that basically means they're not significantly different, both of these data sets. And you can see when you overlay the residuals, I don't see much of anything that is different. In fact, when you plot the residual values, they're almost identical except for some minor differences between Apple and Microsoft right here. Same with the blocks plots. You see pretty much the same type of information between all of these plots. So no reason, no evidence for us to say that these data sets are different. I hope this part makes sense. Now let's go ahead and apply the next technique, which is our dynamic time warping. Just to summarize this again, what we're going to do is warp the time axis, meaning find the optimal alignment between these two series. Maybe there is a difference, maybe there isn't a difference. In this case, I don't see a reason why the warping time should be any different, because if the market goes down for tech industry that day, then I would assume both of these to go down, right? So maybe a day delay, if at all, but I don't expect much of a difference right there. And of course, we are going to create aligned data sets by applying this alignment, and then we are going to apply our Mann-Whitney U test. And then we'll visualize. And again, key insight or p-value, we're going to get 0.6. It's not significant, of course. That basically means it's much greater than 0.05, so there is no significant difference between the two data sets. Although you'll see that when you calculate the correlation between the Apple and Microsoft after time warping, it goes from 0.685. Previously, when we just did, even prior to the naive test, if you look at the Pearson correlation, one of the first things we did in this code, we got about 0.685. And now we will get 0.834, which means the correlation improved, which further tells us that the series are very similar when timing differences are removed, right? So that's one key insight. And one thing you should remember is that this dynamic time warping does not remove autocorrelation. It removes timing differences. So we're testing whether the return magnitudes are different, like in our stock returns, like the magnitudes are different when patterns are matched in time. And it doesn't matter what the autocorrelation is. So first, let's do the DTW comparison right here. And again, let's go ahead and run this. And let's see, we are calculating the DTW distance and then the warping path between the two time series, and we're going to plot those, and we are going to look at the plots. Did I run this whole thing? Yeah, right there. So if you look at the comparing the series, the distance is 28.56. Frankly, I have no clue what to make of that value, but I usually, the first thing whenever I do DTW, I look at this white line right there, which is nothing. I mean, we're plotting Microsoft index and Apple index, and we are plotting that. If there is a significant warping that's needed, then this line would actually have like some squigglies in here. Right now it's almost a straight line. That tells me, I mean, this line actually tells us how to warp, and there isn't much warping needed. If this looks wonky, that tells you that there is a lot of warping that's needed. So this is a first indication that there is no warping that's needed. And of course you see this, basically the original time series and also the aligned series, they kind of look almost the same. And here Apple aligned after the time warping and Microsoft aligned. The correlation right there between these two is 0.834. Previously we had 0.68. So they are further highly correlated compared to prior to this warping. And I added some notes so you can actually follow what's happening in the plots over there. And now that we did the warping, let's go ahead and do the U test, right? So we haven't done that. So that's what we're doing, Mann-Whitney U test on the aligned data sets. Okay, and if you look at the aligned data set, again, huge statistic. If you watched my last tutorial, this usually doesn't mean much unless you look at the p-value. And in this case, the p-value is much higher than 0.05, which tells us these two data sets are not significantly different. If you notice that, all the tests that we have been performing, they consistently tell us that they're not significantly different. This is a good thing. The last thing you want is things are being drastically different when you go from one test to the other. This improves our confidence that these two data sets are not that different. Okay, so I added process here. I should have added text. I'll add that after the tutorial. This is for Bootstrap, by the way. The next step, and I got so excited to record this video and release it before it's too late, because some of you asked questions. Sometimes I overlook little things like adding a title. Okay, so this is the Bootstrap process, and how do we do that? Well, we combine the series data. We combine both the data because we are not doing paired Bootstrap. That's a different test. If you want, you can do that. We are doing like a single Bootstrap test right here. So we concatenate, we add, combine both the Apple and Microsoft returns into one long series. And we resample it in chunks, like take consecutive blocks of 10 days, for example, like 50 to 59, 10 days, 200 to 209, another 10 days with random starting points. So you take these and then don't shuffle the individual points. Then you lose your autocorrelation, any autocorrelation that you may have, right, in your data. And then you create Bootstrap samples, which is basically you combine these blocks to make a new time series of the same length. And you split back into two groups. Split this back into two groups because we have two groups. And calculate the test statistic. Now find the difference in means for each Bootstrap sample. And then if no true difference exists, of course, our observed difference should fall within this distribution. So key insight, p-value, we get 0.99. That's a very high p-value. That means the data sets are not different when we perform this Bootstrap test. So let's go ahead and run this part and look at the results. And again, we are taking the mean of series 1, mean of series 2. That's our original difference of means in the original data. And then we are combining the whole thing, and we are actually looking at where is the Bootstrap differences right here. And I think we're not calculating the statistic here. We are doing that in the next block, so which is okay. Let's go ahead and look at the p-value is 0.96 right there, Bootstrap p-value. Where are we doing the p-value right there? Yeah, so yeah. And when you look at the data looks almost normally distributed, and the observed difference is 0.002. It's literally right around the median or mean value. I think I was plotting the median value right there. and it's almost identical. So it can't get any close to the center as you can see right there. So let's go ahead and perform the final comparison of all of these and write a quick summary. So the summary of all approaches, we have naive, Mann-Whitney, all of these, the p-values are so much higher than 0.05. That tells us the difference between the two time series is not significant. That's what this false basically means. It's not significant. So we can have no evidence that the two values are different. So this is how you perform a for a time series. This is how you perform a statistical test. It's basically Mann-Whitney U test that we have been doing, except we are accounting for the autocorrelation or any time like a time difference, like time warping, for example. There are a few other techniques, but this is probably the top 2 or 3 that at least I would like to talk about in this short tutorial. I really hope you found this to be useful. And again, if you have any such questions about any topic in this series, please leave your feedback in the comments. I may not respond it because I get a lot of comments for a lot of videos, and sometimes they're too much for me to go through. Well, not to go through to answer, but I do go through some of those actually, and if they align with the topic, I'll find time to record a new video and on short notice and try to squeeze that in. So thank you guys very much, and again, please do subscribe if you haven't already done so. Thank you.